So in this lesson, I will try to cover the most important topics, the theory topics from this linear algebra textbook. And Professor Strand, who wrote this textbook, actually kind of put these slides together. So these are not my slides. These are the slides that the author prepared. Now, the important concepts that we all would like to understand is, if you have a matrix, where do we use this matrix? This matrix could be representing an algebraic system of equations that we have to solve. This matrix could be representing the network of rows that we want to understand. It could just be a resistance and capacitance network. It could be a stiffness matrix in the finite element technique, or it could be the matrix resulting from the meshing in boundary element technique. At the end, what we want to do is, we have this matrix, which is an array of numbers, rows and columns. We need to manipulate this matrix efficiently. So what are the various ways of manipulating matrix? Now, what I want you to understand is, if you have this matrix A, this matrix A can be decomposed into columns and rows. So basically, what we have is, this is a column. This is a column representation, column. And then this is the row representation. So you have a matrix, and what we want to do is, we want to decompose this as a column and row. Now, why is this important? Because in last class, we talked about the dependence and independence of vectors. Now, let me give you a very simple example. Imagine I have a matrix 1, 2, 3, 1, 2, 3, 3. Then I have 2, 4, 6, 2, 4, 6, and maybe I have a matrix 4, 5, and 7. So I have this matrix 1, 2, 3, 2, 4, 6, and 4, 5, 7. Now, if you look at this matrix, understand the second column is an integral multiple of the first column, and the last column is an independent column. So basically, what I have here is, if I were to find the rank of this matrix, the rank of this matrix is going to be 2. And now what I want to do is, I want to decompose this matrix into its column and row format. Just bear with me. Let me change this software, because this is not working the way I initially anticipated. So, what I want to do is, I want to show you this one. The PDF 1, 2, 3, 2, 4, 6, 4, 5, 7. Now, what I want to do is, I want to represent this matrix into columns and rows. So the way it works is I'm gonna have columns here and I'm gonna have rows over here. So first column, I would say it is 1, 2, 3. And if I want to, if I want this column to be repeated over here, then what I need to have is, I need to have first row, first column, second row, first column, third row, first column. Then I need to have second is 2 times the first, so basically 2 times 0, and then basically this will be 1, 0. And then this is going to be again 4, 5, 7. So the idea is somehow we take this matrix and decompose it into its column and rows representation so that this entire matrix can be viewed as these basis vectors, say B1, B2, multiplied by these weights W1, W2, and W3. Another decomposition is A times LU, where L is a lower triangular matrix and you have an upper triangular matrix. The third decomposition is an important decomposition, which is Q times R, where Q is an orthogonal matrix and then R is upper triangular matrix. Then this S is a very special matrix. This is called as the symmetric matrix. Now, the important advantage of symmetric matrix is the eigenvectors are perpendicular. But please understand, eigenvectors and eigenvalue problem is only present for square matrices. Eigenvalues and eigenvectors do not exist for rectangular matrices. So for that, what we have is we have singular values. Singular value decomposition is again similar to eigenvalues, eigenvector decomposition. The only difference here is you have something called as the left singular vectors. So these are the left singular vectors. Left singular vectors. And here you have right singular vectors. And these matrices are called unitary matrices, which means if you were to take U transpose U, which would be same as V transpose V, and that's going to give you an identity matrix. So these are called the unitary matrices. Now here is one example. So for an example, this matrix is 3. As you can see, is a symmetric matrix, which means you have these terms at the diagonal and you have the terms which are at the off diagonal, they are the same. The most important advantage of a symmetric matrix is the eigenvectors are perpendicular. If you take any matrix and if you try to find out, it's a square matrix. If you try to find out the eigenvalues and eigenvectors of this matrix, you will notice, first of all, those eigenvectors are not going to be perpendicular. Sometimes the matrix, if it's rank deficient, then it will not have the eigenvectors equal to the number of rows or number of columns. So it is very, very difficult in randomly to pick up a matrix that has perpendicular eigenvectors. But the beauty of the symmetric matrix is the eigenvectors are going to be perpendicular. And why is this perpendicular eigenvectors important? Let me give you a very simple example. Imagine that I have x and y axes. I have x and I have y. When I draw any vector here, so if I say this is my vector here, this is my vector here, I can find out its component on x, I can find out in component of y, and I can find out these independent components because my basis, in other words, my I and j unit vectors are perpendicular. Please understand, if my basis vectors were not perpendicular, then there is a possibility that some component of I would be part of some component of j. So if I have perpendicular basis vectors, or if I have a coordinate system where the basis is perpendicular, it makes my life very easy, because no matter what the vector is in I direction, it cannot be resolved onto j direction. So if you have a vector, say for an example, this is 5 units, this is 5 units, and say this is 3 and this is 4. So if this is 3 and this is 4, this 3i cannot be resolved on any factor on j axis. So I and j's are completely independent. Same thing happens with this Q matrix, and this is again an orthonormal matrix, because please understand, you have cosine and sine and cosine. So if I consider this is my first vector, if this is my second vector, if I say x1 transpose x2, this gives me cosine of theta, sine theta, and then I have sine theta, cosine theta, negative sign. So if I take the dot product, this is the dot product, it becomes minus sine theta, cosine theta, plus sine theta and cosine theta. So what I get is 0, which means the dot product is 0. And dot product is 0, which means those two vectors are perpendicular to each other. The other thing I want to see here is, what is the determinant? If you look at the determinant of this matrix is cosine square plus sine square. So the determinant is 1. What that means is this is an orthonormal matrix. So if you believe what Professor Strand says, then these orthogonal matrices Q's are the queens of linear algebras, and symmetric matrices F are the kings of linear algebra. Now, what I want to do is, this is the same concept that we talked about earlier, but I want you to understand, if you want to multiply a matrix and a vector, you can think about it like this is the basis vector multiplied by the weight. This is the basis vector multiplied by the weight, and this is the basis vector and multiplied by the weight. Now what that means is, this is very important, this AX, the resultant, will be in the span of these basis vectors. So once again, what it means is, if I were to plot, I give an example. Let's take just a simple example. 1, 3, 2. So this means 1 unit in x direction, 3 units in y direction, 2 units in z direction. So for an example, what we have is, we have maybe this vector somewhere over here. This is the vector. If I similarly plot second vector, something like this, and if I similarly plot this third vector, this entire space that is spanned by this vector is actually, let me show you this space. This is this space. So this is this space. And the solution AX will be a point in this space. So if I were to look at the solution, this is going to be my solution AX. And this is very, very important. If you have a matrix, you are multiplying that by a vector as if you are taking the column vectors of that matrix and multiplying those by the individual weights. This picture gives us understanding of the concept which is called as the column space, and we talked about it. This is the first column, second column, third column. So what we have here is this is the column space of the vector. Now if you look at this particular problem, I want you to understand, can someone tell me what is the column space of this matrix? So what is the column space of this matrix? So my question to you all is, what is the column space of this matrix? I'm still getting used to this software. So what is the column space of this matrix? I want you to know 1 plus 4 is equal to 5, 3 plus 2 is equal to 5, and 2 plus 1 is equal to 3. So what that means is the third column space is the linear combination of the first column C1. So this is C1. This is C1. This is C2, and C3 is equal to C1 plus C2. So I have C3 is equal to C1 plus C2. So can someone tell me what is the column space of this matrix? The column space of this matrix is 2, because the third column can be represented as the sum of the first basis vector and second basis vector. What does that mean? It means if I were to plot the first vector, if I were to plot the second vector, and now if I decide to plot the third vector will be in the plane that is spanned by these two vectors. Everyone understood this? So the column space of this matrix is 2, and it's a plane. It's a plane. Now, please understand, column space of a matrix is same as the row space of the matrix, which is the same as the rank of the matrix. So if you were to look at the rank of the matrix, of matrix A, you will see the answer is 2. Now, how do we find out this column and row representation? And earlier, I just went ahead and showed you the decomposition, but the right way to do that is something like this. So we have the matrix, and I will show you. Let's see 1, 3, 2. So I have this matrix 1, 3, 2, 4, 2, 1, 4, 2, 1, and 5, 5, 3. So and then I have this 5, 5, 3. So this is my first column E1. This is my second column C2, and this is my third column C3. So first, what I'm gonna do is I'm gonna grab this column, place it over here. I'm gonna grab this column, place it over here, and now I want you to think about the decomposition which we have. I have 1, 3, 2, 4, 2, 1, 5, 5, 5. So now I want you to note first row, first column gives you 1, first row, second column that gives you 4, first row, third column gives you 5, second row, first column gives you 3, second row, second column gives you 2, second row, third column gives you 5, third row, first column gives you 2, third row, second column gives you 1, third row, third column gives you 5. What?
Then it should be 5 by 3.
5, 5, yeah, 5, 5, 3, right? 5, 5. 5, 5, 3, right? So no, 5, what is it? 5. What was this? 5, 5, 3, yeah, this is correct. So, yeah, yeah, I will repeat it. This is actually very important. So what I'm trying to do is, I'm trying to show you, I have this matrix A. And I want to decompose this matrix as some columns and some rows. I want to decompose this as some columns and some rows. Now, how do I do this decomposition? To perform this decomposition, first I try to find out the independent columns. So can you see that my first column 1, 3, 2 is independent. 4, 2, 1 is independent. So what I'm going to do is I'm going to place those columns C1 and C2 over here. Everyone understood this? The last column is dependent on the first and second column. Do you agree with me? What is the relationship with the last column? Do you agree with me? This is the relationship. Last column is equal to the weight 1 multiplied by the first column plus weight 1 multiplied by the second column. So this 1 and 1 went here. So this one indicates that this is the first column which is independent. This one here indicates this is the second column which is independent, and this last column in this matrix indicates that this column is summation 1 times this plus 1 times this. Okay, I need to make sure that everyone understood. You have a matrix, and the problem here is right now we are looking at a matrix which is a 3 by 3 matrix. But when you look at an image data, image is at the end of the day it's a matrix. If you look at a big neural network, that again is a matrix. If you look at Netflix, if you look at the Netflix price, wherein they are trying to rank, it's a big matrix. And lot of these columns in that matrix, they are functionally dependent on the other columns. I'll give you a simple example. You have a user A. User A likes maybe Tom Cruise, maybe some other movie star like Wayne Johnson, or maybe some other movie star like Keith Richards and all. So there is a high probability if you look at the second person, and if that second person likes Tom Cruise and Keith Richards, then there is a possibility that that person would like mean Johnson. So there is some correlation. It could be a full correlation or it could be a partial correlation. So this column times row representation tells me that what are the features in that data set that are independent and what features are dependent. Why these features are important? Because at the end of the day, when you are trying to do a machine learning or when you are trying to do a face recognition, when you are trying to do a handwriting recognition, what are you looking for? You are looking for some features that are independent, that comprise the data. And then you try to find out a relationship matrix that how other features are dependent on these base features. If you will understand this. So whenever this is column times row representation, is an important decomposition when you are looking at the data size. Now, if all these three rows is very important to know. If all these three columns are independent of each other, if all these three columns are independent of each other, then the column representation is going to be the first column, second column, and third column. And this matrix would be an identity matrix. Are you understanding this? But when you are looking at data, you are never going to get the data columns or data rows that are completely independent. A very simple example. If you, for an example, if I want to do a face recognition, face is not going to be rectangular. I haven't seen anyone with a triangular face. Face is not going to be hexagonal. Face will be either oval or circle or some deformation of the circular section. So which means you are going to have circle as one of the features that is going to be common in all the faces. That's why when you solve the problem, which is called eigenfaces, you will see the first basis vector that you capture from this face data to show you a circular pattern. That is exactly how you detect whether it's a cat or dog, because what you do is you grab the independent features and then see how many independent features in this image match with the independent features in this image. And that is how you can do sort of pattern matching and then machine learning. Okay. One thing that goes without saying, that if you look at this row matrix, the rank of the row matrix is also 2. So if you take this matrix and say rank R, that is going to be 2. And clearly the rank of the column matrix is 2 as well. So this is very important point in linear algebra, that if you have a matrix A, if the rank of the matrix A is 2, if you decompose this into column times row, the column matrix will have rank 2 and the row matrix will have rank 2. So basically that is what you should remember. So you have a matrix, every matrix can be decomposed into column times row. And this is nothing but the discussion where column C, they are the basis for the column space and rows are the basis for the row spaces of A. And the last class, I kind of tried to talk about what I mean by the column space and what I mean by the row space. So everyone remembers column space and row space, the discussion that we had in last class? Does everyone remember? Okay, so I'll give you an example. So 1, 0, 0, 2, 1, 0, 0, 0, 1. So if I were to look at this guy, this is the column space. This is column. So which means if I say this is my 1, 0, 0. This is the first basis vector of column space. If I want to plot the row space, I'm going to focus on 1, 2, 0. This is going to be 1, this is going to be 2, and this is going to be 0. So this will be the row space. So this is C1 and this is R1. And we can plot these in when we have a 3 by 3 matrix. As the dimension of matrix increases 4, 5, 6, it's difficult to plot, but at the concept remains the same. Now, then comes the concept which is called as the null space. So null space is basically if you have a matrix A, and then there is some vector x such that when I multiply this vector by this matrix, I get zeros. And then this x is considered to be in null space. Now, this requires a little bit discussion, and I want you to understand. Let's say if I have a matrix 1, 2, 3, 4, and I multiply by this vector, say 0, 1. So this is my matrix A, and I multiply this vector. What does matrix vector multiplication achieve? Matrix vector multiplication gives you another vector. You agree with me? First row, first column gives me 3. Second row, first column gives me 4. So I had this vector 0, 1. After multiplication, it got transformed into 3 times 4. Everyone agrees to this? Okay. Now imagine I have a vector somewhere here, which is a non-zero. Just imagine 0, 0. If I multiply this vector 0, 0 by this matrix, what do I get? I get 0. Similarly, there is a possibility that there is a number A and there is a number B. When I perform this matrix multiplication, I get 0, 0. Everyone agrees? Then this vector is considered to be in the null space of this matrix. Which means if you take that vector, multiply that by that matrix, what you get is 0. That is the meaning of the null space. Now, one thing I want to tell you, and this is actually super duper important, is if you think about the matrix A, that matrix A, say it has rank R. This can be considered as the summation of rank 1 matrices, and there are total R matrices. So I will show you what I mean by that. So imagine if I have a matrix 1, 0, 0, 1. What is the rank of this matrix? Rank of this matrix is 2. Do you agree with me? This can be represented as 1, 0, 1 plus 0, 1 will be first row, first column, second row, first column. Actually, I will write this like this. First row, first column, second row, first column, first row, first column, second row, first column. This will be so let's first row, first column, second row, first column. So now what I want you to do is, I want you to see this map. This is 2 rows, 1 column, 1 row, 2 column, 2 row, 1 column, 1 row, 2 column. So finally, when I multiply this, I'm gonna get a 2 by 2 matrix. You agree with me? When I perform this multiplication, I'm gonna get a 2 by 2 matrix. Do you agree with me? Let's perform this multiplication. First row, first column, 1. First row, second column, 0. Second row, first column, 0. Second row, second column, 0. Do you agree with me? Same thing over here. First row, first column, 0. First row, second column, 0. Second row, first column, 0. Second row, second column, 1. Do you agree with me? And when I add these two, what I get is 0, 1, 0, 1. Are you with? Everyone understood this? And this decomposition is very important. So what I want to tell you is I want to repeat this because this is the basis of singular value decomposition. Understand? I have this matrix. This is an identity matrix. If I were to take the rank of this matrix, this column and this column, these two columns are independent. So the rank is 2. A rank 2 matrix can be represented as sum of 2 rank 1 matrix. Check this out. The way I did this is first row, first column, 1. First row, second column, 0. Second row, first column, 0. Second row, second column, 0. If you look at this matrix, what is the rank of this matrix? The rank of this matrix is 1. Why? Because this is just 0. Do you agree with me? What is the rank of this matrix? Rank of this matrix is also 1. So what has happened? I had this matrix. And this matrix is symmetric. This matrix is symmetric because if you forget the diagonal terms, off diagonal terms are one and the same. What I did, I decomposed this symmetric matrix as the sum of rank 1 matrices. And this is exactly what's going to happen when we look at singular value decomposition. Did anyone watch the videos on singular value decomposition? Or no? Yes?
Yes, sir, we have watched.
Singular value decomposition does. Singular value decomposition takes this matrix and dissects it into its constituent parts. And that will tell you that this matrix, this data, this image, this picture, this neural network can be decomposed, can be considered as this plus all these matrices. Everyone understood this? Then these constitute the weights on here. These constitutes the weights. In this particular case, the weights are the same, which means what this is telling me that this first column is equally important as the second column. But these weights give me an indication that how much importance is given to this matrix. How much importance is given to this matrix. And similarly, you have all these matrices. Now, this is the crux of data science. If you think about the signal decomposition, if you have a periodic signal, if you want to decompose the periodic signal, what you do is you use Fourier series. What does Fourier series do? You have a periodic signal, and then that periodic signal is decomposed into sum of sines and cosines. Similarly, now you have this matrix. This matrix is expressed as the sum of its constituent parts. So this is similar to the Fourier series, except this is working on the data. It's not working on the continuous periodic signal. So this is like SPD is considered as data-driven Fourier series analysis. Because what it does, it takes the data and that data gets sliced and diced into its constituent parts. And then based on the weights, you can decide which component of that data is important. Okay, there is a question. Let me see what is the question. Oh, okay. That's the plane. So I want you to understand this. Column times row representation is very important because it gives us sort of the decomposition perspective on the matrix. Now, where this column times row decomposition is useful, believe it or not, when we studied linear algebra in our undergrad, we studied something as row reduced echelon form, and that is nothing but the row decomposition of the matrix that we looked at. So I don't know if you did it, but when I was in undergrad, I solved a question like given a matrix, convert that matrix into its row reduced echelon form. So what you have to do is you have to perform the algebraic manipulation on the matrix and finally express that into a row reduced echelon form. Why do we have to reduce into this echelon form? Because it's very easy to solve the linear sets of equations when the matrix is in row reduced echelon form. So again, this column times row decomposition is very useful when we are trying to solve the linear equations, when we are trying to understand the characteristics of the matrix. But again, for some reason, if the matrix is ill conditioned, what do I mean by ill conditioned? If their eigenvalues are widely spaced apart, or if it is rows and columns are close to each other, so the condition number of the matrix is not good, then it's considered as an ill condition. So in that case, finding out row reduced echelon form is tricky because of the numerical stability. Now, one thing I want you to think about it is I briefly talked about what is the geometric significance of Ax is equal to 0. Ax is equal to 0 means that you have a vector x. You have a vector x, and once you multiply a matrix by that vector x, what you get is a 0 or the null vector, or you get 0 or you get a null vector. And why is this null vector important? Because null vector is if you take all the null vectors corresponding to that matrix, that formulates something called as the null space of the vector. Now, what is the meaning of this null space of that vector? If something is in the null space, no matter what you do, you won't be able to get to that point. That is what it means. So if a vector or a point is in the null space of that matrix, no matter what you do onto that matrix, you are not going to get to that point. And why is this important? I give you a very simple example. Imagine GPS, or I don't know if you drive, you use Google Maps, or if you use Waze, or any software that you use for path planning or route calculation. Some routes are possible. So basically, if you want to go from point A to point B, there is route A, route B, route C, route D, and so on. But all of a sudden, if there is an accident, or if there is maybe a signal breakdown, or if there is some type of an investigation, or if that road, there is some road work, the road is closed, what that route planning will do is it will avoid that route and it will go on to the other route. At the end of the day, that algorithm is solving a matrix. At the end of the day, that algorithm is solving that matrix equations and giving you the optimal route. When you have a block or a physical obstacle, what it means, that is the null space that no matter what you do here, no matter whatever route you want to take, you cannot get there. So you want to avoid it. So that is how a null space can be physically interpreted. Another example, I will give you apples and oranges. Okay. Have you thought about this equation? That, and actually I was thinking about this equation. Imagine 3 apples plus 4 oranges is equal to $3. 2 apples plus 7 oranges is equal to minus $8. Which means if you want to buy those apples and oranges, the vendor has to give you those apples and oranges and give you money. Everyone understood this? If you try to solve this problem, you will get some meaningless answers, like you will have to pay $2 for apple and minus $3 for orange. What that means is basically if you want to buy something, to buy oranges, you give $2, and to get apple, that vendor is going to give you apple, and then on top of it, it's going to give you $3. That is basically the significance of null space. Where does this happen practically? I don't know. Actually, it is very interesting. Last year, there were 2 years ago during COVID, there was this crude oil crisis. I don't know if you remember this. So the cost of 1 barrel of oil reached negative value. What does that mean? It means if I go to that vendor, I say I want to buy this barrel of oil from you, he will say, take this barrel of oil and take this $50. So that happened. Okay. So basically, those types of equations, those types of results, they fall into the null space type of concept. Because at the end, what happens is AX becomes 0. For AX to be 0, X will have some positive quantity and it will have negative quantity. Both positive quantities or both negative quantities will not work. So it has to have a positive quantity, it has to have a negative quantity. Only then A times X is equal to 0 equation is possible in terms of commodity trading, or in terms of stock market pricing, or in terms of finding the optimal path from point A to point B, and so on. Now, this is called as the big picture of linear algebra. And this is a completely different way of looking at linear algebra. In undergraduate linear algebra, we don't see this. So let me tell you what that is. What you have is, you have a matrix A. That matrix has a row space and that matrix has a column space. Everyone is clear about what is the row space and what is the column space. Now imagine that you have for the row space of A is orthogonal, perpendicular to null space of A. Row space of A is orthogonal to the null space of A, and the column space of A is orthogonal to the null space of A transpose. So what that means is these are the 4 fundamental subspaces that are spanned by that matrix. Now, if you think about it, and actually I wanted to give you an example, so I will try. So when you look at a data science problem, or when you look at machine learning problem, or when you look at a finite element problem, or when you look at any numerical matrix algebra problem, at the end you are going to have 2 types of problems. The first problem would be A times X is equal to 0, or A times X is equal to, so A times X is equal to B, and A times X is equal to 3. Those are the problems that you are going to have. So the first problem is the problem that we have solved in undergraduate linear algebra. This problem appears is something like this. if you have a spring, on that spring, you apply some force, and what you want to do is you want to find out the respective displacement. That is the problem that is described by Ax is equal to B. Ax is equal to 0 problem is something like this. You have one spring, you have other spring, and now you are applying the force at the center of the spring. You are applying the force at the center of the spring. What is the total displacement of these two springs? Assuming extension of one spring is equal to the compression of other spring, the total displacement is going to remain the same, 0. Why? Because what happened, one spring extended, other spring compressed, but overall the displacement stayed 0. That type of problem is expressed as Ax is equal to 0. Both these types of problems appear in engineering analysis. And the way we look at these two problems is this x is in the null space, and this x, these are nothing but the weights on the column space that gives us the solution. So these are the 4 fundamental spaces of a matrix. So as soon as you see a matrix, it should come to your mind that this matrix has a column space, this matrix has a row space. If I find out the null space of A is going to be perpendicular to it. If I find out the null space of A transpose, it is going to be perpendicular to the column space. Everyone kind of got this big picture. And the thing is, I tell you, the challenge here is these concepts are quite theoretical. But when we try to look at the actual application of it, for example, when we try to look at the compressed sensing, when we try to look at the eigenspaces, all these spaces will become extremely important. I give you a very simple example. Imagine what I have is I have this huge data, okay, and again I don't have enough memory to store that data. Then what can I do? I need to perform some type of compression. If I want to perform some type of compression out of this huge data, which chunk of data I should keep and which chunk of data I should get rid of. So in those particular cases, these spaces will tell us that, hey, in this matrix, these numbers or these rows or these columns are the most important columns that you should capture, transmit, and then perform some type of mathematical manipulation to reconstruct the original data set. If you have used something like WinZip, WinRAR, or I don't know if you have seen that series, which actually Silicon Valley. I don't know if you have seen that series on Netflix or HBO. It's a series on Silicon Valley. The whole series is about that startup is trying to develop this compression algorithm. Those algorithms basically are dependent on these spaces. So what you do is you have the data set, you identify the most important subspaces of the data, just retain those subspaces of data, delete everything else. That subspace you carry forward, either you save it or you transmit it, and then at the receiver side, when you decompress it, from those subspaces, you reconstruct whole data. Everyone understood this? So when I talk about the actual MATLAB examples, I will get back to this and I'll show you how. This is the row space, this is the column space, this is the null space, and this is how it is used. But I want you to understand that this actually is a big picture of linear algebra. If you have a matrix A can be used in 2 cases. Matrix A multiplied by a vector X gives you another vector B. Matrix A multiplied by some vector x gives you 0. If that is the case, then it's a null case. And in the first space, it is actually the weights on that vector. Okay, now what I want to talk about is this is exactly that we talked earlier. If you have a matrix A that can be decomposed into B's and C's, which is sum of rank 1 matrices. And the rank 1 matrices, I want you to understand the representation is you have B1, B2, all the way to Bn. These are the column spaces. These are the rows. And if you take an outer product, so for example, if you say B1, C1, B2, C2, Bn all the way to Cn, what you get is these are nothing but rank 1 matrix. Rank 1. And the important decompositions that we talked about, there is an LU decomposition, lower triangle, upper triangle, QR decomposition, where Q is the orthonormal, R is the triangular, symmetric matrix, wherein you have orthonormal, this is the diagonal matrix, and this is the transpose. And then what you have is you have this eigenvalue decomposition. And finally, the most important is you have this singular value decomposition. So singular value decomposition is the workhorse of all the data science. Everywhere you see a data science problem, everywhere you see machine learning problem, everywhere you see face recognition problem, believe it or not, you are using singular value decomposition. So we are going to focus a lot on the singular value decomposition. Now, what I want to do is, I want to give you this simple exercise, kind of show you simple exercise, wherein you have 2x plus 3y is equal to 7, 4x plus 7y is equal to 15. And what you can do is, you can multiply the first equation. You can multiply equation 1 by 2 and then subtract it from the second equation. If you multiply the second equation by 2 and subtract it from the second equation, what you land up with, you get this set of equations. You agree with me? Now here, as you can see, this matrix is in triangular form. What is the advantage of this matrix being triangular form? Is the solution for y is given to us. I can substitute the solution for y in equation 1 and find out the solution for x. So I don't know if you took a C, C++, Java, some type of class, programming class, and performed this matrix type of matrix with the manipulation. But when I was a student, we were asked to write a program where we give a matrix and a vector, and we have to find out the solution of the simultaneous equation. The way to do that is basically consider the pivot element. You look at the pivot element and then look at the ratio, multiply the first row by the ratio and subtract it from the second row, and recursively perform that to the end that you have this lower upper triangular matrix. And with that upper triangular matrix, you get the solution very easily. And that is how the simultaneous equations are solved in numerical linear algebra. But if you look at this matrix, what we have here is nothing but, in other words, we took the matrix A, performed an LU decomposition, and used this LU decomposition to solve the set of equations. So that is where the LU decomposition is used. If you look at this matrix, this is nothing but the LU decomposition of the matrix A. Now, the next part is you can actually extend this if you were to implement this using a computer algebra. And to be honest with you, this is a recursive process, so you can write a for loop and perform this very easily. So the idea is take these matrices, convert those into a upper triangular form and lower triangular form, and then use the upper triangular matrix to solve the linear equation. Now, the next important part, which we have already touched upon, is how do we know whether two vectors are perpendicular? Two vectors are perpendicular as long as their dot products are zero. The two vectors are perpendicular as long as their dot products are zero. And how do we know if two vectors are orthonormal? So basically, then what you do is, if you have a matrix which is orthonormal, if you take the transpose of the orthonormal matrix and you multiply that by the matrix itself, then you will get an identity matrix. So this is something I would encourage you to remember, because this term, this is something is very useful when we solve the linear algebra problems, or when you try to attempt the numerical linear algebra using mathematics. So please understand, this is a very simple example, that if you have orthonormal columns and if you were to take the transpose of the matrix, multiply that with the matrix itself, you are going to get an identity matrix. And this is an example. If you take this matrix, look that in MATLAB, and then if you calculate QT transpose or QT, you can look at it, that gives you the inverse. So basically Q1, Q2 are orthogonal matrix, and their products are also orthogonal matrix. And some of you are taking the robotics 1 class. Remember, this is the rotation transformation that we have been talking about in robotics 1. Cosine theta 2 minus sine theta 2, sine theta z, cosine theta z, 0, 0, 0, 0, 1. This is the rotation about z. This is an orthonormal matrix. So if you look at the eigenvalues of this matrix, you will notice the eigenvalues are 1. Now, one important numerical scheme that is used for orthogonalization is called Gram-Schmidt. And again, I'm not going to talk about the actual technique, because when I was an undergrad, I used to solve a question where they will give us a matrix and they will ask us to express that into a Q times R decomposition. So there is a long process where you have to take each column, orthonormalize it, then find out its corresponding R, and then propagate it. This QR decomposition can be easily done using MATLAB. So basically, but what I want you to understand is A represented as Q times R is giving you a basis Q multiplied by row matrix R. And I want you to understand Q is orthonormal and R is the lower upper triangular matrix. So basically, what you have is you have an orthogonal basis multiplied with series of weights that gives you the true picture of the data. It kind of tells you that if you have this data, how can this data be represented on an orthonormal basis? And I give you a practical example. If you look at the motion of the star, okay, when 200, 300 years ago, when the scientists were looking at the motion of the star, they assumed that the Earth is at the center of the universe. And then when they plotted the Earth-centric view of the trajectory, those trajectories will be very complex. You couldn't find a mathematical expression that could easily describe the trajectories of stars or planets. So what happened? Kepler came. Instead of assuming Earth-centered picture of the universe, he looked at sun-centered picture of the universe. And as soon as he changed his basis, all that was trajectories, they became very easy and he could derive Kepler's laws. This is exactly what is happening. You have a matrix, and that matrix is not easy to visualize or to understand. As soon as you change your perspective, the picture is much easier and clearer. So that is what it means in terms of Gram-Schmidt scheme. So if you have an orthonormal basis, you can represent data on perpendicular basis vectors, and that gives you the true picture, so to speak, in the data. Okay, I'm gonna stop here. And this material is actually quite theoretical, but I would encourage you to kind of go through this material. And it's very important that you watch the videos from 3 Blue 1 Brown and Visual Kernel, because if you have not watched the Visual Kernel videos, it's very difficult for me to explain some of this theory concept, because there they are explained with animations and cartoons. So please, by the time you come next class, please watch the video lectures for Visual Kernel and then start working on the project. And I will solve the project partially in the class. That way you will have an opportunity to ask me questions. Okay, I'm gonna stop here. But if you have any questions, I would be happy to answer.